So I think we'll get started. I want to welcome you all here this evening. My name is Peter Trapp. I'm Dean of the College of Science. I'm delighted that you've all come out tonight. As many of you know, the Frontiers of Science lecture series is the longest continuously running lecture series on campus. It was started in 1967 by Peter Gibbs, who was then chair of the physics department. And in the intervening 52 or so years, it's hosted a great number of very distinguished lecturers from all over the world, including 30 Nobelists. And tonight is no different. We have a fantastic speaker who's going to give us an exciting and engaging talk. I'm going to turn over the formal part of the introduction to my friend and colleague, predecessor, guru, mentor, Henry White. So, without further ado, Henry. I didn't think I'd be standing up here so soon. And truly, it's a privilege and an honor to introduce and speak as University of Twente. I'm going to give you a little bit of biographical information. I'll start this talk. So, Detlef is from Germany. He was educated in Germany. He received a University of Physics, PhD at the University of Harvard in 1992. Postdoctoral fellow at the University of Chicago. In 1998, he was appointed as the chair of physics of fluids at the University of Twente, where he heads a really, truly impressive group. I've seen this firsthand of roughly, I don't know, I may embellish this, about 75 scientists and students at all levels. Truly impressive. And his research is in the area of fluids. I just say fluids in general. I guess I could say fluid dynamics. It covers this area A through Z. I mean, it is absolutely unbelievable experimental work, top theoretical work, simulations, applications in all areas of engineering and science. It is really remarkable. Detlef is a highly recognized physicist. This year he received the Planck Medal. This is the highest award. I'm reading from the website of where these awards are described. This is the highest award of the German Physical Society for extraordinary achievements in theoretical physics. Congratulations. This must be relatively new, right, this year?
This year.
In 2018, the Balzan Prize for outstanding achievements in the field of humanities, natural sciences, culture, as well as for endeavors for peace and the brotherhood of man. The Bachelor Prize from the International Union of Theoretical and Applied Mechanics for outstanding research in fluid dynamics. He was awarded a knighthood in the Order of the Netherlands Lion. He's a member of the Royal Netherlands Academy of Arts and Sciences and a member of the United States National Academy of Engineering. And in his busy schedule, he just gave lectures at Harvard and MIT, and he's going out to Seattle for where he has important duties at the American Physical Society meeting coming up. I was very fortunate to squeeze in a day of his time here in Utah. And so with that, Detlef, thank you for coming to Utah and visiting us. Thank you for the collaborations that we have. We overlap in the area of nanobubbles, and I don't know if you're going to talk about any of that today, but it's been fun having discussions with you. Detlef?
Well, thanks a lot, Henry, for the very nice introduction. It's my great pleasure and my great honor to be here. And also it's my great honor to collaborate with Henry and his group. So we had a paper together on nanobubbles, on single nanobubbles, and I learned a lot on electrochemistry and on tiny electrodes on which you can develop a single bubble and do measurements on this single bubble. But today I will speak on a little bit larger bubbles and introduce you to various bubble puzzles. The grandfather of fluid dynamics is Leonardo da Vinci, and many people will have. Can we tune down the light a little bit for better contrast? I mean, many pictures otherwise won't have the full beauty. And wait, because yes, much better. Yeah, yes, good. So this is a very famous painting from Leonardo da Vinci. It's in fact a turbulent vortex, and it's in fact on the textbooks on turbulence. He was the first to describe this cascading nature of turbulence. And the question is, why is there this structure? But he was also interested in bubbles. And he was the first to realize that a rising bubble doesn't go up straight, but it spirals. And well, this is published there. And why so, right? I mean, you would expect that it would go down straight. So a solid ball, when you let it sink in water, goes down straight. And a tiny bubble rising in water would go up straight. But a large bubble spirals. And Leonardo asked a question a physicist would ask. And he reduced this problem. So ask question on data, reduce the complexity of the system. And well, he came up with this question, and which since then was called Leonardo's paradox. And here you see a modern visualization of this with Schlieren techniques. This is the same bubble looked at from two sides. You see the vortex, which is shed by this bubble. And in fact, this vortex interacts with this bubble, and from a certain rise velocity on. So once the bubble is large enough, you get an instability, a linear instability. And in fact, in 2006, people succeeded to calculate this. And this problem posted by Leonardo was only solved then. When is this setting in, and why is this setting in? And it turns out to be the interaction of this bubble with its own vortex. I will, in fact, go to an even simpler case of a bubble conceptually, and this is a single trapped bubble. And this brings me to the subject of single bubble sonoluminescence. So what is single bubble sonoluminescence? Well, you trap a bubble in a flask here. The flask is typically a few centimeters wide. You have a piezo here, and with the piezo, you, on the one hand, trap this single bubble, and on the other hand, you also drive it. So the piezo creates a pressure field, and when the pressure is high, the bubble is compressed. The pressure is low, the bubble is expanding, and so is the bubble oscillating. But once per cycle, that it emits a light. The typical frequencies are 40 kilohertz, and it means 40,000 light pulses per second, and from the naked eye, this is some continuous glowing. It's pretty easy to do, and of course you wonder, why is this the case? Because typical light energies are in the range of 1 electron volt per molecule. It's huge, whereas typical acoustical energies are in the range of 10 to the minus 12 electron volt per molecule. So you have an energy focusing factor of 10 to the 12, and that's very spectacular. So what's happening is that while this bubble is oscillating, once the amplitude is strong enough, it will nonlinearly oscillate, and the collapse of the bubble will be very strong. And you know that when you compress gas, then you heat it up. I mean, you know this when you pump up your bike, you will feel that it is heating. And here the heating is so extreme that the gas will partially ionize, and then on recombination, you get emission of photons, and you see this light. And, well, we wanted to understand this. Well, there had been a lot of speculation on how much can you achieve, what's the temperature. And there was a speculation in physics today can sonoluminescence produce thermonuclear fusion, tabletop fusion, on which there is experience here in Utah at your university. Well, this seemed to be yet another case of tabletop fusion, so very speculative here. And they even made a movie on this. So with Keanu Reeves and Morgan Freeman, it's called Chain Reaction. And this movie they made, in fact, when I was in Chicago. And the characters came to our seminar to see how scientists would behave. So it was very entertaining. Not that they learned much in our seminars. So the plot was a little bit bizarre. Well, the word of sonoluminescence is mentioned various times in this movie. So the idea was that someone would concentrate energy and make a huge atomic bomb-like explosion with this. So tabletop fusion, so cold fusion, so to say. Well, we have a more rational approach. We measure, we calculate, we think and simplify, and we explain and understand. And well, here you see the acoustic pressure right here, and the response of the bubble is seen here, both experimental data and data resulting from the so-called Rayleigh pressure dynamics. I come to this in a second. And here you see that the bubble is really expanding, right here, collapsing, and right here you have this light emission, and then you have some afterbounces, and then the process repeats. And I will show one equation in my talk, and this is a Rayleigh-Placid equation. I show it here. It's a very simple ordinary differential equation. In fact, Lord Rayleigh came up with this, with the basic form of this. And here you see how the bubble behaves. For weak driving, you get this oscillation, but for strong driving, you get this typical behavior with the light emission right here. And well, these are damping terms and driving terms, but the main point is here. You have the singularity right here, which leads to the compression. And well, our strategy was to have an interplay between experiment and theory. So we observe the bubble dynamics, and we observe the light emission. This turns out to be thermal Bremsstrahlung. We also observe the reaction rate. There's chemistry going on the bubble, because when the bubble is collapsing, molecular gases also get heated up. And then it's getting so hot that molecular gases like H2 or O2 split and will form NO and H. And this is all dissolvable in water. And all what remains, in fact, is argon, 1% argon in air. And this is all what remains. And that all we observe. And out of this, we deduce what the temperature is within the models. And when we put everything together, this is the result. So what you put together is the shape stability for the bubble. I mean, all this can only happen once the bubble remains shape stable. You need the diffusive stability, so the guy is not allowed to dissolve. You need this chemical stability, so without argon it doesn't work. So you need this argon for stabilization because molecular gases, they all vanish from the bubble. And you need the energy focusing. And you can put this all together, I mean, without any parameter. And here is the result in the parameter space. So this is the bubble size. The ambient size of the bubble are 0. And this is the driving pressure. These are 3 different cases with different gas saturation. So gas saturation is very, very crucial. Those lines, those data points here, the open symbols are stable bubbles which do not emit light. And these data points are stable bubbles which do emit light. And the lines are our theory without any parameters. We really can ab initio calculate it based on these principles. I won't tell details, but I want to convey the message that this is really under control, and there's excellent agreement between theory and experiment. Nothing mysterious, simply putting together these principles. When we now go up in pressure from here to here, we will jump from this stable branch to this stable branch. And what will happen is that then the temperature will jump because for weak driving, you don't have this accumulation of argon here. You only have this accumulation for strong enough driving on this branch. So here you see the fraction of argon which is in the bubble. Here it's very low. And here on this other branch, it's very high, nearly 100% argon. You start off with air, but because of this chemical reaction, you rectify the argon, and argon now has an adiabatic exponent, polytropic exponent of 5/3, because it has no internal degrees of freedom. Molecular gases have lots of internal degrees of freedom, and therefore the heating or the energy goes into these internal degrees of freedom. Argon doesn't have it. Argon can get very hot, and in fact, it gets typically 15,000 Kelvin. This is what we predicted here, this 15,000 Kelvin, and that was this prediction here, down here, and you see that this prediction is much lower than what people had predicted before. So in the first data point was not single bubble sonoluminescence, but multi-bubble sonoluminescence, so people would have some acoustic bars at many bubbles, and they would put ultrasound on it, and then there is some light emission, but the temperatures are relatively low. And then came the hype with single bubble sonoluminescence, and people speculated that this would be 10 to the 8th and thermonuclear fusion and so on. But then people would get more reasonable, adding more and more effects. So that the gas would be, the gases would have internal degrees of freedom, that water, vapor would jump into the bubble, and so on. Thermal damping, and then here we have conversions around 15,000 Kelvin, and I was very happy that a few years later, my friend Ken Susslik, yet another chemist from Urbana-Champaign, he measured indeed 15,000 Kelvin. And that's the temperature, and that's enough to emit light, but clearly not enough for thermonuclear fusion. So I view the single bubble sonoluminescence as the hydrogen atom of cavitation and of acoustic bubbles. It's a single isolated bubble, and you can do one measurement at this single bubble because you trap it, and you can keep this bubble alive for many days. We just discussed, Henry succeeded to do one measurements at one molecule, and well, here we did measurements at one bubble, but it's simply stable under these conditions. Well, when the hydrogen atom was understood, the atomic physics wouldn't stop. You would go to more complicated atoms, you would go to molecules and condensed matter physics, and so did we. We started off, we learned tremendously from this, and then we started off to other things, and I will tell about these other things. I will tell you about the snapping shrimp, I will tell you about inkjet printing, I will tell you on nanofluidics, and drug and gene delivery, ultrasound diagnostics, impact, and many other things. And these are all spin-offs from this fundamental research which we did. Right? I mean, these days there's lots of pressure go towards the applications. I mean, all these are applications which we had no idea of that they existed. They popped up somehow naturally, and we learned on this system tremendously, and it was very useful to do this fundamental research. And so let me start off with the snapping shrimp. This is on cavitation in zoology. And what is a snapping shrimp? Well, here you see this animal. It's about 2 centimeters long, or 2 or 3 centimeters long, with this tremendous claw here, and it makes sound. And I will let you hear the sound. So here you see the soundtrack. Sounds like popcorn. It's very noisy. It's broadband. And this animal is tremendously unpopular with the US Navy. So first of all, it disturbs underwater communication because it's so broadband. And second, this noise has been used in Pearl Harbor by the Japanese to hide their submarines. And so this animal was really unpopular, and people wondered, why is this animal doing it, and how is it doing it? What people thought is that it is some kind of mechanical vibration. So it has this claw, it closes this claw very quickly, and then it would be mechanical vibration of this claw. But well, I saw this soundtrack, and I had seen many soundtracks from bubbles, and I said, well, this looks like a bubble. They didn't believe, the zoologists, that the bubble would be evolved, so we decided to do experiments. So what we did is we would trap this animal, and we would look at this animal with a high-speed camera, and we would listen to this animal with a hydrophone, so that it would snap. We had to tickle it a little bit, and then at some point it would get angry and it would snap. And this is what we listened to. This is a sound as function of time, and with this prominent peak here. And this is what we see. So the claw is closing, and then you see indeed this huge bubble. We now must correlate this high-speed movie with the sound, and this is what we do here. So here the claw is closing, no sound whatsoever. Here the claw is fully closed, and you would expect that there would be some mechanical vibration, but you see no vibration whatsoever. Instead, you see a bubble, and once the bubble is collapsing, you get this prominent peak of sound. So what you see is cavitation noise, the noise of a cavitating bubble. Well, we model this. So here's the pressure reduction. So what's happening is that the water is pressed out of the claw, and this is a high velocity jet, 30 meters per second. And high velocity means low pressure. And then there's always tiny nuclei in the water, and these tiny nuclei in the water would react to the low pressure, and they would grow, and at some point the pressure is normal again, and then the bubble collapses. And it's just as the collapse in single bubble luminescence, there the energy goes into light. Here, in fact, the energy goes into shockwave emission, and I'll come to this in a second. So this is the pressure, and this is the response of the bubble. So the bubble grows once the pressure is low and collapses. And right here, you have the emission. You get the singularity, mathematically speaking. So the same singularity which leads to the energy focusing in single bubble luminescence. And you wonder, why is this animal doing it? And here, the animal is giving its answer. So it wants to eat. It wants to live. So what it does is it shoots this bubble against prey animals. So you see a poor prey animal. And then the bubble is collapsing, emitting a shock wave. And with this shock wave, the prey animal is killed or stunned, and then it's eaten up. So this bubble, the animal simply wants to live. It's an acoustic weapon of this animal. And one question, when we found this out, one question, of course, I got is there also a light emission at this? And, well, I got this question so many times, and when we had this animal, it was easy. So what we would do is we would put a photomultiplier next to this collapsing bubble, and then indeed, we would see light emission, not as strong as with single bubble luminescence, because the bubble, as you saw, is not perfectly spherical. But we did get light emission, and then we gave it the name we came up with a name for this. We called it shrimpoluminescence. and so we came up with the name over a beer, and this name made Webster. So if you look up Webster dictionary, shrimpoluminescence is in there, so we gave this name. The cavitation, in fact, had been that high velocities cause cavitation had been known before as this famous problem of ship propellers which create these bubbles. So here you see a ship propeller or propeller from some submarine, and they rotate at very high velocities. And high velocities, as I explained, means low pressures. This means bubble generation and collapse. And these bubbles can, in fact, collapse next to the ship propeller and eat up the ship propeller. And then you get pictures like this. It is still the case that it is this mechanism which limits the velocity from submarines, right? So I mean, there is this big problem, and of course you can design it in a way that the cavitation is a little bit further away from the propeller. And it is also this problem which the British Navy put forward to Lord Rayleigh in 1918. That they were aware of this cavitation problem, and he was supposed to solve it to help the Royal Navy. Well, he couldn't solve it, but he came up what is now called Rayleigh-Placid equation. So this cavitation problem really originates from here. And I'm sure that Lord Rayleigh would have liked this sonoluminescence, because Lord Rayleigh got this Nobel Prize for the discovery of argon. And argon is so crucial for the stabilization of this bubble. Well, he came up with this equation for the bubble dynamics. And this connection, I'm sure Lord Rayleigh would have liked. Well, this was the first application, or two applications on this. Another application is piezoacoustic inkjet printing. So this is high tech, and we have an ongoing collaboration with OSE. So here you see this inkjet printer. This is not a printer you would have on your desk. This is professional printer, so these guys cost about 100,000 euro, and it's printing on demand. So book on demand, so really high resolution, high quality, also drawings or art, or drawings for architects or so on. Or when you, with this printer is so fast that it can print a book with the high quality printings of this thickness in a minute or so. So this is what they do with it. The core of this printer are these print heads. And I show you such a printhead in more detail. You see it here. Here you see the ink being pressed in. And here is the piezo actuator. Very similar to what we have in single bubble sonoluminescence. This guy is actuating at a frequency, well, 20 to meanwhile 70 kilohertz, very similar as in single bubble sonoluminescence. And then, say 20,000 times per second, a droplet is pressed out and flying towards the paper or toward other substance. And, well, typical volumes are, say, around 10 picoliter, droplet speeds up to 7 meters per second. And it's a very reliable process. Here you see the printing process with 1 million frames per second. And it works beautifully. So here you see the principle. The pressure is built up, and then some droplet is pressed out. You get this pinch off, and this thing is flying towards the paper. However, from time to time, you get a distortion here. So after billions of successful droplets, you get a distortion of this type. And then later, it can break down altogether. Sometimes it recovers, but often it breaks down. And this is, of course, a total disaster, because then certain droplets will not be printed. And, well, what's going on? And they put forward this problem to me. I totally incidentally found this problem. They approached me, and, well, I was thinking of our snapping shrimp, and what's good to solve a problem was a general thing: watch and listen. Watching means high-speed imaging, and listening means we measure the acoustic response of the nozzle. And the finding was that the cause of this failure is an air bubble which is entrapped into the channel. So what is happening here you see the correlation. So this is high-speed imaging. Here you see the distortion around droplet 28. And here we have a signal, the acoustic signal integrated, minus the reference signal, and you see around droplet 28 there is this distortion, and the origin from the distortion is a bubble, which you see here. So here you see the entrainment of the bubble, and the bubble is growing, and then, well, depending on the size, whether it's below resonance or above resonance, it's finding one or the other position in the nozzle. The bubble is entrained, and then you have acoustic oscillations, and then you have this phenomenon called rectified diffusion. So then the pressure is low, the bubble is large, and then gas, which is dissolved in the ink, will go into the bubble. Well, when the bubble is compressed, some gas will go out, but it's oscillating, and then depending for strong driving, the growth mechanism will win, and then the bubble will grow further and further, and at some point it will block the nozzle. So here you see this, and clearly there is no printing anymore. And, well, how to get rid of this problem? Let me briefly mention this. So the only way to get rid of this problem is what I call the Microsoft solution. So what's the Microsoft solution? Well, turn off the device, wait a minute, and turn it on again. And the reason why it works is that these bubbles diffusively dissolve without driving in about a minute. This is the time scale they take to dissolve, and then the bubble will dissolve, and then you can turn it on. And what is now done in this printer, this color wave 600, which I showed you, is that every single nozzle is used to monitor the bubble. So the piezo is used not only for the driving, but also for monitoring. And when we see the bubble at an early stage, we turn it off, and then the printing of that nozzle is taken over by some other nozzle, all electronically and computer controlled. And then we wait for dissolution, and then later we use that nozzle again. And this is how this problem is overcome. And it's absolute high tech, and well, bubble dynamics is very, very crucial for these printers. Well, we do other things. So we also do stroboscopic imaging of this with a stroboscopic method. So here you see the printing of the nozzles, the pinch off right here. So we can resolve time steps down to 10 nanoseconds and spatially up to 1 micrometer. Well, I get these beautiful pictures here. So this picture was one of the pictures, nature pictures of the year from 2014 out of our paper. And it's a Nature scientific picture. And I found it pretty remarkable that it emerged out of a collaboration with industry. But it was the scientific picture of the year. Well, I mean, it's beautiful. It's stroboscopic, and it's absolutely reproducible. But we also made models, and here you see a numerical model for this. I won't go into detail of this. And here you see experiments. The color is the velocity. You see it's pulled back thanks to capillarity, and we have this one-to-one comparison. The model is a lubrication approximation, which is very cheap. I mean, you can, well, there is commercial software, but well, these commercial software often don't think about the problem. Here, we use the symmetry of the problem and can calculate it very cheaply, no parameter. And this is, of course, very useful. You see this tiny difference here. The origin of this tiny difference is air friction. So in the numerics, we didn't put in air friction, but it's so precise that we can really see this difference here. This, when jetting, the droplet, it experienced some air friction, and therefore the experimental guy is a little bit slower than the numerical guy. And with this code, we can now predict what would happen with other viscosities. Of course, the inkjet company, once they want to improve the ink, well, viscosity is a parameter, and they don't want to have the case where it's this pinch off here. They want to keep the integrity of the droplet, in this case, so they must use high viscosity. So we can do numerical experiments and tune the properties of the ink numerically, and this is, of course, much cheaper than doing experiments and trying various things. Well, up to now, I showed you bubbles which were a problem, but there are also beneficial bubbles, and this is for local drug delivery and local gene delivery with cavitating bubbles. So here I show you a cavitating bubble. We make this by a laser. We blow, in fact, a hole in the water with a laser, and then create this bubble, and the bubble is expanding and collapsing, and it's collapsing towards the wall, because the wall introduces some asymmetry, and you see this jet here, which goes towards the wall, and this jet exerts huge forces. So here you see the jet, also here, and you get radial forces from this jet, and these forces can be used for cleaning. So when you go for ultrasound cleaning of your glasses to the opticien, then you put it in an acoustic bath, and it is this mechanism which will clean your glasses. But this is also used for cleaning in the wafer industry. So the wafer industry, they have the problem, it must be ultra clean, and how to achieve this? Well, they use this method here. And it can also be used in biological context, as I show you here. So what we did here, these are all cells on a surface, and we had, in fact, a bubble collapsing here, the jet would go towards the wall, and here all cells are erased and detached. Those cells, the red one, they are dead, and the green one, they are alive, but they took up some fluorescein. And the reason that they took up fluorescein is that the shear forces exerted by this collapsing bubble were so strong that they could open the membrane, and then, in this case, fluorescein could enter. But in reality, of course, you want to have some drug or some gene entering the cell. So this is bubble collapse-induced jet, shear-induced detachment of these cells. So this is the principle here. And here I show you the cells with electron microscopy. We zoom in further and further, and you see these little holes. And when the holes are small enough, some fluorescein or some drug can be taken up, and then it heals again. Once the hole is too large, of course, then we will just die. Well, other cases of beneficial bubbles. This is for ultrasound diagnostics. Most of you will have seen images of this. This is simply medical ultrasound. Frequencies are now 3 megahertz. And the contrast of the picture is often not good enough. And it can be enhanced by putting in bubbles. So here you have a case without bubbles and with bubbles, and the contrast is much, much better. And it's a heart chamber in this case. And well, in case there's a medical doctor, they will see there have been infarct right here. And this is possible by adding the bubbles, because the bubbles reflect ultrasound. So bubbles, they oscillate, but they also reflect ultrasound. And in this sense, they enhance the contrast of these bubbles. Well, you may be getting afraid of bubbles in the body, that they may coalesce and then form big bubbles, and clearly big bubbles in the bloodstream is nothing you want to have, so that you must avoid, and it's avoided by coating the bubbles. So we produce these bubbles and we coat it with some protein, and then the bubble is very stable and can't dissolve, or only over many, many hours. And this is how the bubbles are injected into the body, and they are beautiful contrast enhancers. Well, the question arises how to make these bubbles. So for optimal contrast, these bubbles must be monodisperse in size. And here we developed some so-called co-flow device with which we make monodisperse bubbles. So this is some airflow. This is water. The water is dragged along through this nozzle, and you get these very monodisperse bubbles, which we can adopt in size to the medical ultrasound, that you get bubbles close to the resonance for optimal contrast. And then this is coated here. So here you see this. It's all monodisperse. And we put it in some polymeric solution, and then these bubbles are coated and are stable. So this is a spin-off company from our group, and the PhD student who was doing this is now selling this coated air for a huge amount of money. So one injection, I think, is about 100 euro or so. It's all coated air, but it gives beautiful pictures. So the research on improved ultrasound diagnostics require high-speed imaging. I said that the medical ultrasound is around 1 to 10 megahertz. And when you want to visualize things, and I have shown you many combinations of acoustical signal and optical signal, and when you really want to see what's going on, you need a high-speed camera. And a high-speed camera means at least 10 to the 6 frames per second. So better 10 to the 7, sorry. We need 10 to the 7 to be able to resolve the dynamics, what's going on here. And this brings us to Utah, in fact, because there was one camera developed by Corden. This is this camera in the 50s here in Utah. And this is not a Canon, this is a camera. And that was developed to visualize the explosion of the atomic bomb. And that was able to have 25 million frames per second and 130 frames. And the principle, in fact, is this turbine with a rotating mirror. It's driven in atmosphere in helium, and then a film negative is put here, and with some optical tricks, you get 133 frames. However, the problem with this camera is that you have, because of this film negative, you don't have lots of flexibility. You must develop your film. This takes forever. And you have also very low light sensibility. Well, with atomic bomb, this is not a problem. You have enough light. But for medical imaging, it is a problem. And also for research, you want to have, of course, lots of flexibility. So what we did is we threw out this film, and we replaced it by 128 CCD camera. In fact, this brought me for the first time to Utah when we spoke with this company called, and I think they still exist, and they made these turbines here. This turbine is, by the way, rotating with 20,000 rotations per minute. It's really extremely fast, and it's only possible in a helium atmosphere here. Because in air, you have so much friction that you can only rotate this guy such that you would have 1 million frames per second. But we need this 25 million frames per second, so therefore we have to go to helium. We could also go to H2, but this was a little bit shaky for obvious reasons, so we wanted to avoid this. Well, we operate with helium. Unfortunately, the price of helium went up quite a bit. Well, when we started this, I mean, one shot was about 10 euro, but now we are at one shot is about 200 euro because of the price of helium. But well, that's how it is. Well, here this is the imaging. We call it Brandaris. So Brandaris is a Dutch lighthouse on a Dutch island, first built around 1600, and then it was later equipped with a rotating Fresnel lens system, and well, very famous in the Netherlands. And to honor the Dutch, I mean, I myself, I'm German, but to honor our neighbors, we called it Brandaris. And well, with this, we then get bubbles, pictures of oscillating bubbles like this. So here you see the interaction of these oscillating bubbles, shape instabilities, and we can compare with theories. And we can also see these medical bubbles interacting with cells and so on. Well, let's come to yet another application, or potential medical application of bubbles. This is needle-free injection with very fast jets. The principle is shown here. It's a capillary, and we shoot a laser pulse in here. So here you see a hydrophobic coating, and this hydrophobic coating forces this meniscus to be in this shape. And when we shoot in a bubble, the bubble will form, and a shock wave of this bubble will hit this meniscus and lead to this jet. So here you see what's going on. You shoot in the laser, you get this jet, and this jet, in fact, can get very high in velocity, up to 1,000 meters per second. So here you see this jet, absolutely reproducible, I mean, this is supersonic. I mean, it's pretty remarkable. You shoot a laser, and the strength of this laser, which we need, is not stronger than a laser pulse like this, but it's, again, this focusing, thanks to the shape of the meniscus, which leads to this pulse. Well, you can, of course, wonder what happens when you put in more laser power, and I show you this. Well, sometimes experiments go wrong, and well, here we put in a little bit too much power, and the shock wave was so strong that the whole device was broken. And what do we do with this? Needle-free injection. So there are existing methods for needle-free injection, but they have all kinds of disadvantages. I won't go into this. But with this method here, we have a tiny jet which would go through the skin, and it's highly focused, very high speed, very well controlled, and the target material is skin. And we take artificial human skin. It's called artificial human skin because it's artificially grown, but it's real human skin. This is some type which is used in the Netherlands as the standard model for skin. So Yoshi Takawa, the postdoc, went to Leiden, collected the skin, freshly grown, and then with some bag, which he uses for transporting food, so with some cooling, he would come and have the skin, and then we would shoot into the skin here. So under the skin we put in some gelatin as substitute of tissue, and then we shoot here this jet through the skin, and this is the first visualization of a needle-free injection. Well, here you see this picture. It also works with chicken skin. This is what we tried first. For pigs, it doesn't work. So pig skin is too thick, and well, then we didn't succeed. But human skin works, and then we inject a small amount into the tissue here, and it's so small that you can't feel it. Well, I didn't volunteer, but well, I mean, it's clear that this hole is so small that you can't feel anything. Well, I now showed you various ways how to create a bubble, injection, or this cavitation, but there is another way to create a bubble, and this is impact. And here I show you an experiment, so impact on liquids. And here's an uncontrolled experiment, impact experiment, with a huge splash, and you will see that there's beautiful bubble dynamics here. And we do the controlled version thereof. Well, artists are also, in fact, stimulated by that. We do the controlled version. We have a tank, and then we have a disk, and we would pull this disk through this air-water interface and see what's going on. And you see this here. So air, water, and we get this void formation, we get this crown, and we get this collapse, and we get this tremendous jet. Well, the jet in this case will fall back. I mean, we can, in fact, when we pull strong enough with the disk strong enough, we can easily get a jet from here up to the ceiling. So it's really a very violent event, and it is also energy focusing. Here you see another movie. So you get this beautiful crown, and where the crown is partly closing. This is thanks to the air outside. Then you see this jet shooting up and then breaking down again. And here you see the series of events. First, the void creation, and you realize that there's hydrostatic pressure, and then this void by hydrostatic pressure is pressed together again, and you get this singularity here. And well, then out of the singularity you get a jet, and you get this entrainment of a bubble. So you wonder what has this to do with the collapse of a spherical bubble? Well, it's so to say the two-dimensional version of this. You have all these layers with this air disk in between, and many air disks next to each other. And mathematically, the collapse of this three-dimensional bubble is nearly the same as the collapse of these disks. What is singularity formation for the bubble, which leads to single bubble sonoluminescence and this emission of light. Here, the focusing is brought to the jet. The focusing as it's in 2D is not as strong as in 3D, but it's mathematically it's really very, very similar and basically the same type of equation. Well, we also calculate this with numerical simulations, and they show that you see the same here. This collapse and the singularity, we can very nicely describe it. What's also the case is that you in fact get airflow. So airflow first goes inwards when this is formed, but then you get reversal and you get outwards airflow. So when you throw a stone in water, the void is formed, and when the void is formed, air goes inside, but I will place this again, at collapse, the air bubble is compressed, and then the air reverses and goes outside. And this here is visualized by our PhD student with smoke from a smoke machine. So he bought a very simple smoke machines for parties and so on, and visualized this, and really could show the reversal. And we could also calculate and measure this velocity, and it's supersonic. So can you imagine? You throw a stone in water, and you first create a supersonic air jet going out, and then later this other jet. I found it pretty remarkable, and again, it is a singularity here. So the airflow reverses, and you get this supersonic thing. Well, there are also less pleasant applications for bubble collapse and this jet formation, and I show you here. So this is a boat, and well, this was a boat, to be precise. So a torpedo is shot on this boat, and naively you would think that this torpedo is shot on the boat. This is not the case. So what they do, the military people, they shoot the torpedo under the boat, and then they create a huge bubble here, and this bubble expands, and then the boat will be bent a little bit in this way, but then the bubble is collapsing, and this jet is forming, and it is this huge jet which will break the boat. And I will play this now again, and then you can see the series event. You see deformation, but now comes the jet, and it is jet which is bombed. So this is how the boats are done. This is, by the way, a Dutch boat. This is a controlled experiment, some old boat from the Dutch military, and they wanted to visualize this. It's all bubble dynamics. Well, up to now, I have impact of droplets on solids. Up to now I'm on water, but now impact of drops on solids, and this will give the bubble deformation tooth. So it's a drop impact on paper in this case, and well, you will have seen impacts of this type. And here I show you impact of a drop on cotton, and it looks very, very differently. And well, in this case, the liquid is blood. So we did experiments for the Dutch Forensic Institute. They were interested in blood spreading around to reconstruct the murder scene. And well, here in the US, I think there's a big market for this here. In fact, you want to reconstruct details of what happened from the blood spreader. And well, here you see impact on superhydrophobic surfaces with beautiful dynamics. And bubbles play a major role. I will come to this. So the phase space is huge. You have drop velocity, diameter, viscosity, surface tension, roughness, temperature, air pressure. And air pressure, you wonder, why is air pressure relevant? Well, the air pressure is relevant because of some entrainment of a bubble. So here you see the splashing under 1 atmosphere, and under 0.2, no splashing. So the reason for the splashing is the ambient air here. And well, how come? And well, here you see entrained bubble, and I come to this. Well, the reason is once the droplet is falling, pressure builds up under the droplet, and this pressure acts back on the droplet, and you get this deformation. And you get this entrainment of a bubble right here, and you get this dimple formation. And this high pressure air inside this will just prior to impact be pressed out and lead to the splash. So it is really this bubble which causes the splash. And we visualize this with high-speed color interferometry. And with this, we could directly see this air bubble under the droplet. So the principle is that the water droplet is falling down, and we have interferometry. So with the light, the signal is coming here. It's reflected at the air-glass interface, but also reflected at the air-water interface, and then you get interference, and you get pictures of this type, side view, bottom view, and out of this interference pattern, we can reconstruct the profile here. So you see the profile, and you really see that a tiny bubble is entrained under the impact. Note, this is millimeter scale, as the droplet is millimeter scale, but this is micron scale. So it's really tiny, but very crucial for the splash. And well, here we compare the entrainment of the bubble for various cases. So on the y-axis, you have the velocity of the impact. So basically the height from which you let the droplet fall. And on this axis, we have the volume of the bubble as compared to the volume of the droplet. So you see right here, we have not much of an entrainment. And this is for very low velocities. When you have your droplet and you gently deposit it on a surface, not much of an entrainment. when you are down here, you smash the droplet against the surface. Also not much of an entrainment, but in between you have the optimum of entrainment right here. And this is experiment and this is simulations, and they very nicely agree, and you have scaling laws and so on. And this also turned out to be very relevant for high-tech, for immersion lithography. So how to make wafers? Well, wafers are done with lithographic methods, and to improve it, you have immersion lithography. So in between the glass lens and the wafer, you put in some liquid. And you really don't want bubbles in there, because then the optical signal is totally screwed up. And this was work, in fact, done in collaboration with this company ASML, and they produce the stepper machines to make the wafers. Well, I would like to close with impact on sand, and then I go now from the nanoscale to the astrophysical scale. So here's a major impact event, asteroid impact on the Earth. And well, nobody has seen this event. There's only speculations, but there are traces. So traces of this impact event on the moon in this case with craters. And note the central peak here, right? So right here is central peak. Traces on Mars here, and traces on Earth. Here, this is from Arizona. And the geophysicists were beautiful speculation on what was going on. And well, we again decided to make controlled experiment. Well, how to do this? So we did it on sand, and very soft sand. So what we would do is we would blow air through the sand, and then would let this the sand settle, but then we had it in a controlled initial state, and it would also be very, very soft. And then we would let this ball fall on it, and you see that the jet is higher than the initial release height. And here you see what's going on with high-speed imaging. You see this tremendous jet which is formed out of this sand. And then you see the clustering inside the jet. It's falling back. And you get this eruption here. And here we see the different phases, 3 events. So first you get the impact, which creates a splash. Then a jet is formed, and finally you get this granular eruption. And from the side you see what's going on, exactly the same as in a liquid. Void formation, void collapse, 2 jets, one going down and one going up. So what's crucial is that it's really very fine sand, and that you fluidize it, and then you let it settle, and then you can really do this in a controlled way and also do calculations on that. So here's a little calculation. You see the splash, and what you also see here is this little jet formation, but it's the quasi-2D simulation, and we didn't include air, so the jet is not particularly pronounced, but the principle is the same. Well, one question is, once you have sand of this type, does the sand bed support the weight? So here we've prepared sand, and we put in some weight, and then we will see what's going on. And see it here. You see the sand is not strong enough to support the weight. And in this sense, it's the analog of the impact of an asteroid, because the asteroid, of course, had much more energy than our projectile. However, the surface is also more stable. And the ratio between the strength of the material and the strength of the impact is a dimensionless number. And in this sense, experiments of this type can directly be compared to the impact of an asteroid. And well, here we see that this is the sand bed doesn't support the weight, and this gives another analogy, and this is a famous dry, quick sand. Here is another case of dry, quick sand, the muse from Lawrence of Arabia. And it's in fact very similar conditions as in our lab. So we blow air through the sand, and then the sand settles, forming this dry quicksand, very soft sand. It doesn't support weight, as you saw. So this guy is vanishing in the sand. So very similar as in our lab, but the time scale is a little bit slower here for dramatic reasons. So you see also the crater formation here, just as in our case, right? But it's slowed down, right, for dramatic reasons. But well, the conditions are all very similar. So I must warn you, this movie won't have a nice end here. However, well, no nice end of this movie. However, as you will see in a second, a beautiful crater formation here. So there it is. And you now know how it develops, right? Well, I hope to have shown you that out of single bubble sonoluminescence, there are various applications of snapping shrimp, impact, inkjet printing, nanofluidics, drug and gene delivery, impact on sand also, and many other things which also popped up. I mean, the nanobubble in a sense in which I collaborate with Henry also is kind of a spin-off from this. And the research on sonoluminescence has been fundamental research. So I heard about it, and I went to my postdoc friend and colleague, Michael Brenner, after I had heard about it, and well, we started to discuss, what is it? I mean, we didn't write any guide, we simply started to discuss what could it be, and this is how it developed. And many applications popped up thanks to that, though they hadn't been foreseen. And they keep on popping up. And well, I hope to have made clear that the physics of bubbles is broad and fascinating, from nanoscale to astrophysical scale, experimental, theoretical, numerical, and both fundamental and applied. And I put in this bubble puzzle article, so I wrote this last year, put in quite some work. It's 50 pages, but it's easy to read, from bubble puzzles, from fundamentals to applications. It's, so to say, my bubbly biography. Most examples I showed are in there, but many, many more on electrolysis, on nanobubbles, also on using bubbles to explore under the ocean where oil reservoirs are. This is also all done with bubbles, and is all in there. And well, with this, I would like to end. I end with the splash, which in fact is coming from impact on a very thin layer, leading to this beautiful splash. And with this, I would like to end, and thank you for your attention. And I'm very happy to take questions, obviously. So.
Yes. Thank you very much. That was wonderful, very interesting. I'm sure Detlef will welcome questions from the audience. Over here, Tom.
How different is the behavior of a bubble in water versus a completely non-polar liquid?
No difference. So, I mean, it's, well, from fluid dynamics point of view, it is the dimensionless numbers, right? I mean, and then all these material properties, viscosity, surface tension, or so on, that you would then, in fact, translate to non-dimensional numbers, Weber number, Reynolds numbers, and so on, and then it's all the same. I mean, once the non-dimensional numbers are the same, it's the same behavior. So.
Question up here.
With those injections through the skin, what kind of volumes can you deliver?
Well, that's the problem. I mean, the volumes are tiny. Right? So, I mean, this is, in fact, picoliters, and say 10 picoliters or so, and this, for some medical applications, is not enough. So. Pardon, what is?
What sort of adaptations do the snapping shrimp have to avoid cavitation damage?
Well, I mean, they shoot the bubble far away from this claw. So it's a jet, and they don't let the bubble cavitate close to its own body, but they shoot it, and you saw that it's a little bit away from the animal, so it shoots against the prey animal, and that prey animal will get the cavitation damage, but it's far away itself that it won't be damaged itself.
So is there a limit to the energy of
Well, there is a limit, and the limit is, I mean, this 15,000 Kelvin. The reason is that once it gets very hot, you get more and more degrees of freedom. I mean, first you get vibration and rotational degrees of freedom, but at some point you get ionization. And once you have ionization, in fact, the number of degrees of freedom is so huge that the polytropic exponent will be 1, and therefore you don't get further heating. And that's the limit, and that's why we don't get much higher than 15,000 Kelvin.
What do you expect the bubble behavior to be different if you shrink the bubble size from micron to nanosizes?
Well, I mean, again, it's a dimensionless number, which is relevant. And whether inertia is dominant or whether viscosity is dominant. And most phenomena I showed you are inertial phenomena. If you go to a nanoscale, then these inertial phenomena, they don't exist. And then you don't get this inertial collapse and the energy focusing you don't get. I mean, that you get down to a few microns. But once you go to a nanoscale, it's all dominated by viscosity and surface tension. And then, well, this sonoluminescence can no longer occur. So it's all stabilized by that.
For the drug delivery using bubbles, would that require that the drugs be in a gas phase?
Sorry, can you speak up? Sorry.
Would the drug delivery methods require that the drugs you're using be in a gas phase?
No. So the medicine is in fact dissolved, and the issue is to get the medicine inside the cell, and therefore you want to damage the cell and make these little holes so that there's an uptake, but it can be, in fact, it's in liquid form. It's around, so it's dissolved, and then it will be taken up. Yeah, it's a very good question. We tried this, and we have, in fact, we have experiments on that. We do it under some angle. You get asymmetry. So what happens, in fact, I mean, it's an excellent question, and the answer is very surprising. So what you get is that you get impact from under an angle in the sand, and you get the same void formation, and also the same void collapse, and you get a jet. And the jet, in fact, goes back to the direction where the intruder comes from. I mean, you would somehow naively expect that it would go like this, but is not the case. So the intruder comes here, it vanishes in the ground, and the jet goes back, and that introduces asymmetry in the crater formation. And you see this. I mean, most craters have some asymmetry, and we did exactly the same thing in the lab, showing this asymmetry. So I have some movies on that, and in fact, we also published on that. It's very interesting because it's so counterintuitive. Because somehow people think when you have some jet, some intruder, it would somehow go like this, but it's not the case. It goes back. Yeah.
Other questions? Up front there, yes. I see a bunch of hands. Go ahead.
Did you experiment when you did things with sand? There's different kinds of sands. There's the like fracking sand
Yes.
that they do. They have a ball bearing type, very rounded sand. Other sands are angular. Did you have?
Yeah, well, what we did is what's crucial is the size, right? I mean, so you want really very fine sand, and the sand what we had is 40 micrometer grain size. And well, if you go to a larger grain size, then you can't fluidize it so easily. The shape of the sand grains doesn't matter so much. It's the size. The size is very, very crucial. So, and in fact, what's good for this is so-called bird sand. So apparently, when you keep birds at home, you need special sand. And so in the end, we ended up getting bird sand from some shop which was also selling supplies for animal. A problem is indeed breathing, right? I mean, it's so, if it's too much wind, you inhale all this stuff, and that's not particularly healthy. Well, I mean, there was this cold fusion case here, and I mean, there was another case with fusion with sonofusion, and there was a big hype. I mean, I showed you these plots, but it was fake too, right? I mean, so people claimed that out of sonoluminescence they would get sonofusion, and it's a very sad story. By the way, also on publishing in scientific journals, because I mean, I saw the paper before, and it was obvious that this paper was total nonsense. And it had been seen by various referees, and they had all rejected it, but the editor had accepted it anyhow, because he wanted to be in the news. And I mean, it was obvious total bullshit, the paper.
Low bubbles involved with the results of excess energy in cold fusion.
Well, the cold fusion, I mean, well, there was no excess energy, but in the sonofusion case, it's well, there's a bubble involved. I mean, they claimed that they would get, in fact, neutrons out of there. Sonofusion, they call it. Very sad story in many ways.
With the cardiac ultrasonography, what kind of volume is required to be injected with those bubbles, and how long will that stay in the system?
That's also a very good question. So the volume which is injected is, I mean, 5 milliliter or so. I mean, it's very little, but it stays a while. So once you have an analysis of this type, you're not allowed to fly for a week, because once you have these bubbles in the body, you with bubbles, pressure fluctuation. I mean, bubbles, as you saw, respond to pressure, and well, at the plane you get pressurized, depressurized, and they really don't want to run any risk, and they say that you really must not flee. I think it's 5 days or so, and so it lives there for quite a while. I mean, honestly, I think after 2 days it's probably gone, but they want to be on the safe side, and they say 5 days or a week or so you can't fly.
I have a last question. So I actually read Detlef's papers, and it's heavy-duty applied math and theory, a lot of them. This is a compliment. This is a compliment. You didn't see any of that today in this lecture, but you saw these really just extraordinary experiments, just creative ways of thinking about taking a complex problem and coming up with a beautiful experiment. What do you enjoy most? The theoretical part of it, the math, or
the combination?
dreaming up these experiments?
So what I enjoy most is the combination, right? So really combining experiments. I mean, coming up with a simple system. I mean, in the spirit of Leonardo, right? To really boil it down to the essentials, get rid of all complications, boil it down to the essential, like your single nanobubble, right? By electrolysis, and then combining the experiments and the theory and the numerical simulation, so to putting it all together. But what I personally enjoy most is to solve problems. Right? So you have a problem. For example, you had this problem of sonoluminescence. It was a major question. Nobody knew what was the origin. Or we had this major problem of these nanobubbles. Why are these guys stable? And then you want to solve this problem. And I mean, this is the beauty about science. I mean, you solve it, you collect. I mean, it's like puzzle. You have a puzzle, you collect many pieces, they put it all on the table, and you try to put it together. And it doesn't fit. Well, then you try differently, and then pieces are missing, so you do experiments, so you do calculations to add these pieces. What's particularly bad is that, in contrast to a real puzzle, there are pieces on the table which don't fit. Right? So they don't belong to this puzzle. So for example, these are experiments which are wrong, or wrong conclusions. I mean, we discussed this afternoon about, for these nanobubbles, about one case. So this was on the table, and it was simply a piece which wouldn't fit in. And then you somehow must realize, okay, get rid of it, this doesn't fit. But the moment when in your mind all these pieces of the puzzle which are on the table fall together to something beautiful, to a picture, and then you realize that's it. That is the moment where you go for. And you must often collect it for many, many years, think about it for many years, read the literature, all papers, and I read also all the papers to learn about it, and then put it together. And this very moment when you combine and you realize that's it. Right? But and then you realize it yourself, but then you, I mean, when I was doing the sonoluminescence, I mean, I was relatively young, and then I thought, okay, I know that's the answer, that's it. And then you think that other people would immediately believe you, but that's not the case. And I was very surprised by that, but now I understand, because many people thought about themselves, and they somehow psychological don't realize that this is now over and done. So there is some resistance. And then you have to convince your peers that it is the right answer. And this is also part of it. And this this takes then sometimes a few years or so, but then you convince your peers that this is the answer. And this is also enjoyable. Then the community takes this over. But the nicest thing, which I really enjoy most, is the moment to realize, okay, now I understand. That's the solution of the problem. And it's really a combination of all: experiment, theory, numerics, and collecting it all.
That's a great description of science. Let's end on